Hi, everybody. I wanted to talk to you a little bit today about how to deal with bank turns, which is kind of similar to inclines, but also really different. I know we didn't get to it in class today, but I think this video will really capture how to manage those, and they're really, really cool. So let's think about first what a bank turn is. I don't know if you've ever noticed, like when cars race cars particularly go around a track, the track sometimes goes up on a bank and it like goes around at an angle. And what that actually does is it allows the car to take the turn a lot faster than it would on a flat ground. On flat ground, the only force that's really keeping the car in its circular orbit is friction. The only centripetal force is friction. What's really cool is with a bank turn, you don't even need friction to stay in the turn. Even things like exit ramps on highways are slightly banked to help enable you to be a little bit safer taking a turn at higher speeds. It's also how airplanes angle when they fly to get their lift force kind of at an angle. It functions similar to a bank turn. So I'm going to draw an incline first because I want to remind you what we do when we're dealing with forces on an incline. A bank turn looks just like an incline, but we do a very different resolution of the forces. So here's an incline. Okay. So the incline, if you remember, like we did in class, you have the incline, you have the angle theta, you have a thing on it like that. You have the weight acting down, and you have the normal force up. Okay, let's ignore friction for now. So on a bank turn, if we think about a bank turn as part of a circular track and slice it and look at a side view, the side view of the banked turn is going to look very similar. We're going to have the side view, that's the like to the center of the circle. And then the car is going to be sitting on the incline. And just to like make it so you understand, I'm going to draw like these are the headlights of the car. So the car is coming out at you that way. So the difference here is on an incline, the car would be driving up or down the incline. On the bank turn, the car is coming around like that. So the side of the car is what's up or down. The door is going to be on the incline. But other than that, the force diagram is the same. So let's draw the weight acting down, and let's draw the normal force acting up. Okay. On an incline, what we're concerned with is this direction, that X direction down the hill. So when we deal with our components on an incline, we're very careful. I don't think my colors are really going to show up, but I'll give it a shot. We're very careful to say, okay, we want to deal with only X and Y forces. You want to deal with forces that are parallel and perpendicular to the acceleration. And in this case, the acceleration is going to be up or down the hill. It's moving that way. So when we resolve the weight on an incline, we look at a WX and a WY, and that allows us to deal with the forces that affect the acceleration directly, which is along the hill. If you're going in a bank turn, it's not sliding up or down the hill, it's actually staying stationary. And in fact, you could think of this bank turn as part of a circle of radius r. I'm going to draw the radius somewhere else actually, because over here it's going to be in the way of what I want to do. So there's like a circle of radius r. And so the important directions are actually not along the hill and perpendicular to the hill. The important directions are centripetal towards the center of the circle is the direction that we care about. This is like a really weird looking circle. I'm going to erase it real quick. Just do that, do a better job. So basically, this is the direction we care about because that's the R direction. It's towards the center of the circle. And so what you can see here really is a couple of things are going on. That normal force is to some degree providing a centripetal force, pushing the car and keeping it in the circle. And some of that normal force is balancing out the weight and holding it stationary. So rather than resolve the weight into components, on a bank turn, we want to resolve the normal force into components because that's actually the force that's going to be the one that we want to deal with. So I'm going to call that F N Y, and Fnx. Those are our two forces. Fny is going to equal the weight. Those two forces are providing the stability for vertical equilibrium. And then the Fnx force over here, that's what's providing the centripetal force. A little bit of geometry will show you that the hill angle, theta, is the same as the angle up here. You can work that out. So it's that over here. Remember, the hill angle is over here, and you can pretty easily go from here to here with some very simple geometry. So our Fnx equals Fn times the sine of theta, and our Fny equals Fn times the cosine of theta. Okay, and we know Fny is equal to the weight. Okay, so if we know that Fny is equal to the weight, we know that Fn sine theta is providing the centripetal force. So if we come down here and use our centripetal force equation, F net equals mv squared over r. For F net, providing the centripetal force, we put in Fn sine theta but then for Fn, from the vertical equilibrium, we can put in W over cos theta, which is mg over cos theta. So this becomes mg sine theta over cos theta equals mv squared over r. It's mass independent, and we're actually left with g tan theta equals v squared over r. And sometimes people write that as tan theta equals v squared over rg. And this is a really cool result because tan theta equals v squared over rg, what this means is if you have the angle right and the velocity right for a given radius, you can take the turn at a speed, and if you take it at that speed and you bank it at that angle, you don't need any friction to stay on the hill. Your equilibrium is taken care of between part of the normal force balancing your weight, and then the other part of the normal force here is providing the necessary centripetal force to keep you turning in the circle. Same thing as what happens to a plane when it angles its wings. Some of the lift force is directed that way, and some of that is canceling out the weight of the plane, and the rest of it is providing a banking force in a way just to keep it going in a circle. So I hope that's helpful.